Hello dear students, this is our fourth lecture for our course. Today we will discuss random variables. In general, to analyze random experiments, we usually focus on some numerical aspects of the experiment. For example, in a soccer game, we may be interested in the number of goals, shots on goal, corners, kicks, fouls, and so on. If we consider an entire soccer match as a random experiment, then each of these numerical results gives some information about the outcome of the random experiment. These are examples of random variables. In a nutshell, a random variable is a real valued variable whose value is determined by an underlying random experiment. Let's look at an example. If I toss a coin 5 times, this is a random experiment and the sample space can be written as follows. Note that here the sample space S has 2 with power 5 equal 32 elements. Suppose that in this experiment we are interested in the number of heads. We can define a random variable x whose value is the number of observed heads. The value of x will be 1 of 0, 1, 2, 3, 4, or 5, depending on the outcome of the random experiment. A random variable is a real valued function that assigns a numerical value to each possible outcome of the random experiment. For example, the random variable x defined above assigns the value 0 to the outcome t, the value 2 to the outcome th, and so on. Hence, the random variable x is the function from the sample space S to the real numbers for this particular random variable. The values are always integers between 0 and 5. The definition of random variables is a random variable x is a function from the sample space to the real numbers. We usually show random variables by capital letters such as x, y, and z. Since a random variable is a function, we can talk about its range. The range of the random variable x, shown by range x or Rx, is the set of possible values for x. In this above example, the range will be 0, 1, 2, 3, 4, and 5. The range of random variable x, shown by range x or Rx, is the set of possible values of x. Another example. Find the range for each of the following random variables. Number 1. If you toss a coin 100 times, let x be the number of heads you observe. Number 2. If you toss a coin until the first head appears, let y be the total number of coin tosses. Number 3. The random variable t is defined as the time in hours from now until the next earthquake occurs in a certain city. The solution. Number 1. The random variable x can take any integer from 0 to 100. Number 2. The random variable y can take any positive integer from 1 to n. Number 3. The random variable t can, in theory, get any positive real number from 0 until infinity. Discrete random variables. There are two important classes of random variables that we discuss in this book: discrete random variables and continuous random variables. We will discuss discrete random variables in this chapter and continuous random variables in the next chapter. There will be a third class of random variables that are called mixed random variables. Mixed random variables, as the name suggests, can be thought of as mixture of discrete and continuous random variables. We will discuss mixed random variables in the next chapter. Remember that a set A is countable if either A is a finite set such as 1, 2, 3, 4, or it can be put in one-to-one correspondence with natural numbers. In this case, the set is said to be countably infinite. In particular, as we discussed in the first chapter, sets such as N, Z, Q and their subsets are countable, while sets such as non-empty intervals in R are uncountable. A random variable is discrete if its range is countable set. In the previous example, the random variables x and y are discrete, while the random variable t is not discrete. X is a discrete random variable if its range is countable. Probability mass function BMF. If x is a discrete random variable, then its range or x is countable set, so we can list the elements in Rx. In other words, we can write Rx equal x1, x2, x3 and so on. Note that here x1, x2, x3 are possible values of the random variable x. While random variables are usually denoted by capital letters to represent the numbers in the range, we usually use lowercase letters such as x1 or x or y or z and so on. For a discrete random variable x, we are interested in knowing the probabilities of x equal xk. Note that here the event A equal x equal xk is defined as the set of outcomes S in the sample space S for which the corresponding value of x is equal to xk. In particular, A equal S element from sample space x of S equal xk. The probabilities of events x equal xk are formally shown by the probability mass function BMF of x. Definition 3.1. Let x be a discrete random variable with range Rx equal x1, x2, x3 and so on, finite or countably infinite. The function probability of x xk equal probability of x equal xk for k equal 1 to 3 and so on is called the probability mass function of x. Thus, the BMF is probability measure that gives us probabilities of the possible values for a random variable, while the above notation is the standard notation for the BMF of x. It might look confusing at first. The subscript x here indicates that this is the BMF of the random variable x. Thus, for example, bx for 1 shows the probability that x equal 1. To better understand all of the above concepts, let's look at some examples. If you toss a fair coin twice and let x be defined as the number of heads you observe, find the range of x, r of x, as well as its probability mass function p of x. Here our sample space is given by HH and HT and TH and TT. The number of heads will be 0, 1, or 2. Thus, the range will be 0, 1, and 2. Since this is a finite and thus countable set, the random variable x is a discrete random variable. Next, we need to find BMF of x. The BMF is defined as b of x and k equal bx equal k for k equal 0, 1, and 2. We have bx 0 equal bx equal 0 equal btt equal 1 over 4, bx for 1 equal bx equal 1 equal b for ht and th equal 1 over 4 plus 1 over 4 equal 1 over 2. Probability of x for 2 equal probability of x equal 2 equal probability of h and h equal 1 over 4. Although the BMF is usually defined for values in the range, it is sometimes convenient to extend the BMF of x to all real numbers. If x not element in range of x, we can simply write probability of x equal probability x equal 0. Thus, in general, we can write bx of x equal probability of x equal x if x is in Rx or range of x and 0 otherwise. To better visualize the BMF, we can plot it. The following figure shows the BMF of the above random variable x. As we see, the random variable can take 3 possible values 0, 1, and 2. The figure also clearly indicates that the event x equal 1 is twice as likely as the other 2 possible values. The figure can be interpreted in the following way. If we repeat the random experiment, tossing a coin twice, a random number of times, then about half of the times we observe x equal 1, about a quarter of times we observe x equal 0, and about a quarter of times we observe x equal 2, as in the following figure. For discrete random variables, the BMF is also called probability distribution or BD. Thus, when asked to find the probability distribution of a discrete random variable x, we can do this by finding its BMF. The phrase distribution function is usually reserved exclusively for the cumulative distribution function CDF, as defined later in this book. The word distribution, on the other hand, in this book is used in a broader sense and could refer to BMF, probability density function, PDF or CDF. Another example: if you have an unfair coin for which pH equal B, where B is between 0 and 1, if you toss the coin repeatedly until I observe a heads for the first time, let Y be the total number of coin tosses. Find the distribution of Y. First, we know that the random variable Y can potentially take any positive integer, so we have range for Y equal n equal 1, 2, 3 and so on. To find the distribution of Y, we need to find by for k equal probability Y equal k for k equal 1, 2, 3 and so on. We have by for 1 equal b, y equal 1 equal b, h equal b. Probability y for 2 equal probability y equal 2 equal probability th equal 1 minus b times b. by for 3 equal probability y equal 3 equal probability for t and h equal 1 minus b square times b. by for k equal probability y equal k equal probability t and so on until t and h equal 1 minus b with power k minus 1 times b. Thus we can write the BMF of y in the following way: by of y equal 1 minus b with power y minus 1 times b for y equal 1 and 2 and 3 and so on, 0 otherwise. Consider a discrete random variable x with range x, r of x. Note that by definition the BMF is a probability measure, so it satisfies all properties of a probability measure. In particular, we have probability of x is between and equal 0 and 1 for all x, and summation of all probabilities for x must be equal 1. Also note that for any set A is subset from range of x, we can find the probability that x is element from A using the BMF. Probability of x element from A equal summation for probability of x. Properties of BMF: probability of x must be between or equal 0 and 1 for all x's. Summation for all probabilities must be equal 1 for any set A subset from range of x. Probability of x element in A must be equal summation for all probabilities of x. An example: for the random variable y in example 3.4, it checks that the summation of by for y equal 1. Number 2, if b equal half, find the probability for y is between and equal 2 until 5. Probability y for k equal 1 minus probability of 1 minus b with power k minus 1 times b for k equal 1, 2 and 3 and so on. Thus, for number 1, to check that summation of probability of y equal 1, we have the summation for probability of y equal summation from k equal 1 to infinity for 1 minus b with power k minus 1 times b, which is equal by geometric sum, which is equal 1. If b equal half, to find y between and equal 2 and 5, we can write k from 2 until 4 for probability of k, which is equal 7/16. Thank you, and we will continue in the next lecture.